So last time we did this, let me write all the usual stuff. Co-17C, day is the 21st. And so last time we had the following, and I'm just going to give you the brief setup here. We had a forest. We have gaps are going to be G of T. And we have adult trees, that's going to be A of T. And both of these is the amount of area, right? And then we're told that 1 dg dt is equal to negative 0.2 g plus 0.1 a. dA dt is equal to positive 0.2 g minus 0.1 a. We're not going to draw the compartmentals and stuff. We're just going to set up. We're also told, and this makes sense, right, that if the area of the gaps plus the area of the adult trees is constant, right? If the whole area is never changing, then you're just talking about the different proportion of gaps in area that also add up to the same amount, which makes sense if you think about these derivatives here, right? If you add dg dt plus dA dt, well, look at those equations. If you add those together, you're totally going to cancel them out and get 0. So dg dt plus dA dt equal to 0 means that the functions g of t plus a of t add up to a constant because their derivative is 0. And the derivative of the only thing that has a derivative that's 0 is a thing that's a constant. And then we made up a number. I think we said, so we're going to say that g of t plus a of t equal 20, I'm thinking acres. So we have 20 acres of land to use. And part of it's covered with gaps and part of it's covered with adult trees. And the last time I did something, which I feel like is maybe the less usual way of doing it, where I went and then took this equation, solved for G, plug it into there, and then solved this as a separable differential equation, which is a totally fine way of doing it. You'll totally get the right answer if you do it that way. But I think the way most people are looking at this is as a matrix kind of deal where you find the eigenvalues and eigenvectors, which is also a totally fine way of doing it. So let's look at it that way instead. So let's find our matrix. Matrix A is going to be negative 0.2, 0.1, 0.2, negative 0.1. And something I want you all to get used to seeing here is if you happen to see a matrix where one row is a multiple of the other row, which these totally are, right? The first row is just -1 times the second row. That always means that 0 is going to be an eigenvalue. Always. And it could be any multiple, right? One could be 2 times the other one or 3 times the other one. If one row is a multiple of another row, always 0 will be an eigenvalue. And we'll see it when we do this out here, but it's nice to just know that's going to happen. So let's find the eigenvalues. So we're going to do the determinant of negative 0.2 minus lambda, 0.1, 0.2, and negative 0.1 minus lambda. And that's going to be negative 0.2 minus lambda times negative 0.1 minus lambda minus 0.1 times 0.2. And set that equal to 0. Now, if I'm smart here, I can avoid doing some of the mental arithmetic. I'm noticing the following. I'm going to have negative 0.2 times negative 0.1. And that's the same as 0.2 times 0.1. Which means the 0.2 times 0.1 here minus the 0.2 times 0.1 here is going to cancel out. So I don't really need to know that 0.1 times 0.2 is 0.02. Although you could. You could totally just multiply this out and get 0.02 plus 0.1 lambda plus 0.2 lambda gives me a plus 0.3 lambda plus lambda squared and then minus 0.02. And just like we said, the 0.02 and the minus 0.02 are going to cancel out. And then we can factor a lambda out from these two things. I'm left with lambda times, I'm going to write lambda plus 0.3. So we end up getting that both lambda equal to 0 and lambda equal to 0.3 are eigenvalues. It could be, it could very much would be. Thank you. Thank you for saying something. I didn't make that mistake on purpose. I appreciate you saying, James, what's going on here? Yeah, that should be negative 0.3. Good call. All right, so now let's go ahead and find the eigenvectors. So and I'll do it the way she likes to do it because that's what you're doing in class. So for lambda equals 0.3, I'm just taking this matrix here and plugging in 0.3 for lambda. Sorry, negative 0.3. Holy smokes. One of these days. So plugging that in, I have negative 0.2 minus negative 0.3, so plus 0.3, 0.1, 0.2, and negative 0.1 minus is plus 0.3. So, and that's going to be multiplied by the vector we're looking for. I mean, xy, you could write GA, but it's fine. And that's going to be equal to 0, 0. So we're getting, let's see. We're getting 0.1, 0.1, 0.2, 0.2. And again, not surprisingly, both rows should essentially give you the same equation. The first row is giving you 0.1x plus 0.1y equals 0. And I'm not going to write it, but the second row is essentially the same. The second row is 0.2x plus 0.2y equals 0, which gives you the same relationship between x and y. Solving for y, 0.1y equals negative 0.1x, multiply both sides by 10, because who wants to use decimals? Y equals negative x. So for this eigenvalue, our eigenvector is equal to, pick anything you want for x. What is everybody going to pick for x? 1. So what's y have to be? Right. You just get to pick. It's nothing fancier than that. You get to pick. The only times you don't get to pick are if one of them happens to be equal to 0. Then that one is 0 and the other one is 1. But you always get to make a choice, kind of. You could have picked different. You could have picked 2, -2, or 5, -5, but we all picked 1, -1. Let's say this is lambda 1, this is v1. And then we'll do the same thing for the other eigenvalue. For lambda 2 equal to 0, well, we don't even have to change anything, right? The matrix is just negative 0.2, 0.1, 0.2, negative 0.1 times xy equal to 0, 0. And we end up getting negative 0.2x plus 0.1y equal to 0. Solve for y. I like to multiply by 10 just because it helps me see it better. Y equals 2x. So now we pick, you all write down the eigenvector. I'll take a sip of water. Oh, this screen is really dirty. I don't see any cleaner solution anywhere though. Oh well, I guess it'll just remain dirty. There's like a million like cleaning. Like there's a lot of look at it, like every board has its own little cleaning thing, but no square. Well. All right, hopefully everybody is coming up with the eigenvector 1, 2. You can either pick a value of x, you can pick x equal to 1, get y equal to 2, or you can do the thing where you say x is equal to the coefficient of y is equal to the coefficient of x. That works too. All right, so let's write our general solution. So our general solution is, and let's use g and a instead of x and y. G of t, a of t equal to c1e to the lambda 1 is negative 0.3 times t times v1 plus c2. I don't really want to write e to the 0t because 0 times t is 0 and e to the 0 is 1. So when lambda equals 0 is your eigenvalue, you don't really get the the e to the lambda t part. You just get 1 there, and it's c2 times the eigenvector 1, 2. Okay. We need an initial condition to figure out the rest of this, right? So no one told us how many adult trees we're starting with or how much gap area we're starting with. So let's give ourselves a value. Let's say we're going to start with, let's use a new page. Now we're going to solve this system, supposing that G of 0 is equal to 2. Which might not feel like enough information until you remember that we were also told that G of t plus A of t is equal to 20. So if G of 0 is 2, how much does A of 0 have to be? Right, 20 minus 2, 18. So now plugging in t equals 0 and G equals 2 and A equals 18, we're going to get our new equation is going to be 218 equal to C1 e to the 0. I shouldn't even write. I started to write it. Let me touch myself here. Right, e to the 0, which is 1, negative 1, plus C2 times 1, 2. And now we can solve for C1 and C2. So we're going to get that 2 equals 1 times C1 plus 1 times C2. And 18 equals negative 1 times C1 plus 2 times C2. And personally, you could solve for C1 and C2 and plug back in here, but I'm noticing that I happen to have C1 and negative C1 here. So if I just add these equations together, it's really easy to solve for C2. So if we add those together, we get 2 plus 18. C1 minus C1 is 0. And C2 plus 2C2 is 3C2. So we end up getting that C2 is equal to 20 divided by 3. And then you can plug this back into either equation to find the other value for C1. I'd probably pick the first equation because it's got smaller numbers in it. So if I plug in right there, I'm going to get that 2 is equal to C1 plus 20. 23rd seems awfully big, James. No, that's fine. You're right. 2 written in thirds is 6/3. So 6/3 is 2 minus 20/3 is equal to C1. So 6 minus 20 is negative 14/3. That's C1. So our particular solution is going to be, I would prefer to write it like this, as a vector, G of t, A of t, equal to negative 14/3, e to the negative 0.3 t times 1, negative 1, plus 20/3 times 1, 2. Or if you had to separate it into what G of t and A of t were separately, you're just looking at the top entries versus the bottom entries. So here, G of t would equal negative 14/3 e to the negative 0.3 t plus 20/3 times 1. And A of t would equal negative 14/3 times negative 1 is positive 14/3 times e to the negative 0.3 t plus 20/3 times 2 is 40/3. And you'll notice if you were to add these together, what would happen to the e to the negative 0.3 t parts if you added these two equations together? They would cancel. And then what's 20/3 plus 40/3? Which is how much? Right, 20, which is what we said G of t plus A of t always has to add up to. So this is confirming that, oh yeah, things are looking like they're working the way they should here. Okay. The last thing we typically like to ask about this kind of deal is like what's some sort of ratio? Yeah. So the question we really want to ask is the second question here, but I'll ask the first question first. So sorry, I've lost my spot here. Well, yeah. So we might start off by asking what fraction of the total area is occupied by adult trees at time t. This is not terrible to answer. The answer is really just exactly, it's going to be the amount of adult trees divided by the total. What's the total? 20. Sure, you could say it's going to be divided by A of t plus G of t, but A of t plus G of t isn't changing. It's a constant in these situations. So really, that's just going to be 1/20 times A of t, which is going to be, in this case, I mean, I would just write 1/20 times 14 thirds, e to the negative 0.3 t plus 40 thirds. Right. Right. Exactly. And the reason we have them up is because I think they say somewhere like, well, if you, again, in the problem in web work, if you add dg dt plus dA dt, what do you get? Do those equations add to 0? Yeah. So if the derivatives add to 0, we know that the original functions add to a constant. And so you can find that constant by looking at what's happening at time 0. So what's A of 0 and G of 0 in that problem? Great. So we know that the total amount of area we have occupied by gaps and adult trees is 37 plus 3, which is 40. And that won't change because the derivative of their sum is 0. And then the more interesting question here is, what happens to this fraction as time goes to infinity? Well, what's going to happen is the e to the negative 0.3 part is going to e to the negative 0.3 times t is going to get smaller and smaller and smaller. So you've got e to a negative number that's getting larger. And so what happens is, different pen. What happens is this part here is going to go to 0 as t goes to infinity. So we're left with A of t going to 1/20 times 40 thirds, which reduces just to 2 thirds. Some noteworthy observations. Well, if the fraction of adult trees is 2 thirds, let me ask you all, what happens? Oh, sorry. Ooh, I should have been a little more clear here. That's not what A of t is doing. It's what A of t divided by the total is doing. Sorry about that. So in a similar way, if the fraction of space taken up by adult trees is 2 thirds, what fraction is taken up by the gaps? Well, if the adult trees take up 2 thirds of the space, the gaps have to take up 1/3 of the space. Here's why this is interesting. Look at that ratio. The ratio between gaps to adult trees is a 1-to-2 ratio. Look at that eigenvector. A 1-to-2 eigenvector, the one that actually matters, because this one goes away as time goes on and on and on and on. So literally, the one that has the negative eigenvalue, that goes away. And if you just look at the eigenvector for the remaining one, that eigenvector tells you the proportion of gaps to adult trees. So there's one gap for every 2 adult trees. So the gaps take up 1/3 of the space, and the adult trees take up 2/3 of the space. Kind of neat. So that's, if you look back at the notes from, or the lecture from last class, you'll see that we did this problem in a very different way. We did it doing separation of variables, which, although I think might be easier, might not be as difficult. It might not be easier as well. It might be just as terrible either way. Sure. Let's see. All right, 1 second here. So I would point out that problem 7 is very similar to this as far as the procedure. Let's talk about the setup, because I feel like for problem 7, what is probably throwing off most people is setting it up after the setup, I think the rest of it is literally the same process as what we've done here. And then we'll talk about some other things. So here's my version of problem 7, which is a lot of writing. Let's see if we can cut down the writing. Suppose that the drug is administered to, wow, let's see if I can say the words. Suppose that a drug is administered to a person in a single dose, and assume that the drug does not accumulate in body tissue, but is excreted through urine. Denote the amount of drug in the body at time t by B of t. So let's make one of our compartments B of t. And in the urine at time t by U of t. And just to go back and read again, the drug does not accumulate in the body tissue. Okay. And is excreted through urine. All right, I think, okay. So they're telling us that B, and then they say, sorry, so then they say that B at time 0, so the amount of drug in the body at time 0 is 5 milligrams. And the amount of blood, sorry, the amount of drug in the urine at time 0 is 0 milligrams. And the thing that I think is hard about this situation is I'm not great with the biology, right? I don't really know how this works, but I believe what's happening is we've just got kind of an exchange back and forth like this. I think. I'm trying to read this question again, see what's happening here. Suppose the drug is administered to the person. The drug does not accumulate in body tissue, but is excreted through the urine. Note the amount of drug in the body at time t by B of t, and in the urine at time t by U of t. Yeah, I don't even know if we actually need this picture. But I think basically we are just going to have a transfer here where we also have, well, either the drugs in the body or the drugs in the urine. But those are the only two places it gets where we're not excreting it out of the body. It's not going to the blood, in the body, whatever. Biology is not my forte here. It's in the blood, or it's in the body or the urine. What I'm saying is we don't have arrows coming out like that. I think, but I see what you're trying to say, but I think what I think that arrow is actually represented by this here. I think that is like it's going to the urine and then it's going to get excreted out. I don't think you're wrong to want an arrow going out there, but I don't think we have one. I also think we might not actually need this diagram here. It's also fine. So here's what I would say. I'm pretty confident that we have this. Right? Those two things have to add up to 5. And what else are we told? It takes 36 minutes for the drug to be at 1/2 of its initial amount in the body. That sounds like a real useful piece of information. I know that essentially B of t, they're telling you a half-life here. They're telling you that 36 minutes later, you're going to have what you start with. But that means if they're talking about a half-life, we have an exponential growth situation here. So we know that B of t should look something like CE to the KT. All right, let me ask you all a question. If you know that B of t equals CE to the KT, what should U of t equal? Let me circle something super helpful. Yeah. Well, they're asking us, I'm trying to solve the system. They're not asking us to solve it though, right? They're asking us to write the differential equations. Okay, that's fine. So if I take the derivative here, what's dB dt equal to? It's the whole thing times, right, the whole thing, oh, the whole thing times K. So it looks like dB dt is K times B. We'll talk about K in a second here. Right, but you're totally right, Jocelyn. That it's C e to the kt times K. And then similarly over here, du dt, well, it's a little bit weirder, but it's going to be negative C e to the kt times K. Which makes sense again, because, right, if the two things add up to a constant, then the derivatives should add up to 0. So that's just going to be negative K times B. But it is times B, which again, I feel like I've gotten slightly backwards somehow. No, I haven't. I haven't gotten it backwards, but it feels like I have. Because the way I've written this currently, it looks like the amount of stuff going into the blood, the rate of change is positive, or body, sorry. It looks like the rate of change into the body is positive, and the rate of change into the blood is negative. Which, or, holy shit, urine. Body, urine, okay. But it's not. Because what we're going to find here is that when you solve for K, K is going to be negative, which will fix everything. Okay, so let me ask you all, how are you going to find K? Well, they told us something. They told us after 36 minutes, you have half as much as you started with. So we know, and I'm going to leave this all to you to do on your own, that we know that B at times 0, you have 5 milligrams. And then B at 36 minutes later, you should have 2.5 milligrams, half of what you started. So we can use that to first find C and say that B of t is going to equal B of 0 is going to equal C e to the k times 0, which should equal 5, which will give us C equal to 5. So then we have B of t equal to 5 e to the k times t. And then you're going to plug in 36 and get 2.5, and it's going to equal 5 e to the k times 36. And then you can use that to find k. And then whatever that k value is, you're going to plug in there and there. I will point out that k is going to be the natural log, something like the natural log of 1/2 divided by 36. So when you find dB dt, it'll be that natural log of 1/2 over 36 times b, and du dt will be the negative natural log of 1/2 divided by 36 times b. So just pop it in there for whatever value of k you have. It's not too terrible, but it's a little bit weird to set this up. So our setup was totally right, except that really, I shouldn't even have this arrow, right? It's all just going from the body to the urine. Oh, sorry, you can't see the thing. Sorry, you shouldn't have that arrow there because everything's going from the body to the urine. Cool. Once you figure out what's going on, that problem's not too terrible. But it definitely does take not a small amount of mental energy to just be like, okay, what is really happening here? And it really kind of goes back to the importance of reading the question and being able to really interpret what's going on. A lot of these gap dynamic questions are really about reading it and being, okay, what do I really have going on here? All right, let's move along. There were definitely a few people that asked me to talk about the trace determinant method for classifying equilibria of differential equations. So let's move along here. And I want to say, I know, that's what's going on. There we go. So one thing I want to point out, right, is if you were given the following matrix, A, B, C, D. I know it's very generic. And you're asked to, classify the system or the equilibrium of the system. Sorry. Of the system of differential equations. They didn't actually write any differential equations, right? But we all know that when you write this matrix, the assumption that we're making is that, oh yeah, that means that our differential equations are dx dt equals a times x plus b times y, and dy dt is equal to c times x plus d times y. Right? That's what is all. That's all the whole machinery and buildup of that matrix. That matrix means you have all those equations. We're not going to go write them every time because we all know that when you write this matrix, it just means, oh yeah, these are my differential equations. All right, so let's start with some examples here. And we'll kind of approach some of these both ways just so we can talk about how you would see it either way. So let's say our matrix was, sure, let's look at this matrix. A equal to 11, -4, 15, -5. All right, so I'll talk about the trace determinant method first. So in fact, I want all of you to find for me both the trace and the determinant. So find the trace, which we usually label as tau, and find the determinant. Label this capital delta. Trace should be super straightforward. I mean, they both should be straightforward. Trace should be fairly easy to calculate. Okay. Trace 11 plus -5. Determinant 11 times -5 minus -4 times 15, which is what? -55 plus 60, +5. Okay. So something to remember. If the determinant is negative, what do you have? Saddle, always, every time. Determinant's negative, you don't even need to look at the trace. But if the determinant's positive, you can have kind of any of the other things. You can have a stable or unstable node, you can have a stable or unstable spiral, or you could have a center, which is just the spiral where the real part is 0. So how do we figure out what's going on? Well, here's the criteria. So if the determinant is greater than 0, then you need to look at the trace and how the trace and the determinant compare. So first, you look at the trace. If the trace is positive, you have instability. If the trace is negative, you have stability. Always. And if the trace is 0, you have the center thing, which is weird. Yeah. Then, and here's the other part that's kind of weird, you have to compare. And I have to remember what it is. If the determinant is bigger than 1/4 the trace squared, then it's a spiral. If the determinant is less than 1/4 the trace squared, it's a node. That's it. That is literally it. And I guess I should say, yeah, that's really. I'm trying to think. Is there another way of saying that? No. And I guess well, okay, one more tiny thing. And then special case, right? If the trace is equal to 0 and the determinant is bigger than 1/4, well, the determinant would have to be bigger than 1/4 the trace squared if the determinant's positive. So yeah. Then you have a center. So in this case, our trace is positive, meaning we have instability. Well, I should say, first of all, I should say our determinant's positive, meaning we don't have a saddle. And then our trace is positive, so we have an unstable equilibrium. And then comparing our trace and our determinant, well, I should say our determinant and 1/4 of our trace squared, the determinant 5 compared to 1/4 of our trace squared. 1/4 of our trace squared is 1/4 of 36, which is 9, and 5 is definitely less than 9. So we have a node. So we have an unstable node. Is this easier than actually finding the eigenvalues? Depends on your perspective. But sometimes we don't actually know all the values, so we actually kind of have to do this. So there are times when we don't know the values of the matrix. We just know like positive or negativeness. This is where this kind of is more applicable. I like to check. So I'll remind you all that if we actually did it the eigenvalue way, the determinant of 11 minus lambda minus 4, 15, negative 5 minus lambda. Use 11 minus lambda times negative 5 minus lambda minus negative 4 times 15. And that's going to end up being lambda squared plus 5 lambda plus 11 lambda is plus 5 minus 11 is plus negative 6 lambda. And then minus 55 plus 60 gives me lambda squared minus 6 lambda plus 5. And not surprisingly, because this happens literally every time, it's always lambda squared minus the trace times lambda plus the determinants. Always, every time. So what you could do by finding the trace and the determinant, instead of just remembering like, okay, well, the trace is positive, it's unstable, the trace is negative, it's stable, and then this weird delta being bigger than 1/4 tau squared, you can say, well, I can look at that and put it into the quadratic formula really easily. My quadratic formula is going to be lambda equal to negative b plus or minus the square root of b squared. I guess I can write, I don't really need the negative there, but fine. Minus 4 times delta all over 2 times 1. This is what gives us those conditions for if tau is positive, you have instability because the real part's going to be positive. If tau is negative, you have stability because the real part's going to be negative. And here, this is exactly what's leading us to, oh yeah, if tau squared minus 4 delta is greater than 0, you have real eigenvalues because the square root is going to be of a positive number. But that's the same as saying tau squared is bigger than 4 delta, or delta is less than tau squared over 4, which is why you get a node when that's true, because you're just saying the insides of the square root are positive and you get real eigenvalues. Or if you do it the other way, tau squared minus 4 delta less than 0, right? This is going to be a node here. It's going to be a spiral here. And that's going to lead you to tau squared less than 4 delta, or delta greater than tau squared over 4. So that's where that's all coming from. So in this particular example, actually plugging in your values, your eigenvalues are going to be, brain, 6 plus or minus the square root of 36 minus 4 times 5 all over 2, which is 6 plus or minus the square root of 16 all over 2, which is 6 plus or minus 4 all over 2, which is 10 over 2, and and 2 over 2. Oh yeah, both of our eigenvalues are positive. We have an unstable node. That's what happens, right? So there are probably 3 different ways you could go about classifying the eigenvalues. You could either, classifying the equilibrium. You could either actually find the eigenvalues. You could use this trace determinant method. Or I guess you could kind of, I guess there's really 2 ways. Two ways, I would say. You can actually find the eigenvalues, or you can use the trace determinant method. You can find the eigenvalues kind of in a lot of different ways as well. So That's what I would say about that. Let's look at another example. Really, I guess the faster way is going to be what you're better at doing. I think you're probably all better at finding the eigenvalues than you are at knowing the criteria for the trace and the determinant. But if you practice the other one, you can also do it that way. So let's look at like 4 more examples here. Let's see. Let me cross out the ones that we've done. Let's look at this one here. Let's say our matrix is this. 2, -12, 4, -12. Sure, that seems, yeah, I guess that's right. All right, I want you all to find the trace and the determinant and then see if you can classify what's going to be the case. All right, what's my trace? -10. What's my determinant? How much? Is it 24? Cool. All right. Do we have a saddle? Nope, definitely not. No saddles here. No, because our determinant is positive. All right. The trace is clearly negative. So that means we have stable equilibrium. And now are eigenvalues real or are they imaginary? Well, is the discriminant, not the determinant, is the discriminant, right? The part that's under the square root of your quadratic formula, is that part positive or negative? Well, if I look at tau squared minus 4 delta, tau squared, so you can do the thing where you do delta compared to tau squared over 4. I never remember that. But you all have used the quadratic formula a number of times in your life, and you probably remember the b squared minus 4ac part, which in this problem just translates to tau squared minus 4 times 1 times delta. It's easier for me to remember that as well. So if I remember that, I'm just looking at tau squared minus 4 times delta, which is equal to -10 squared minus 4 times 24. And it's going to be a close call, but 100 minus 96 is positive, meaning our eigenvalues are real, meaning we have a node, not a spiral. So we have a stable node, also known as a sink. That's how I would do this if I was asked to do it this way. Let's look at a couple more. Yeah, why don't you all try? Where'd that one go there? Yeah, okay. Try this one. Try 1, 1, -8, 5. Again, find your trace, find your determinant, and then try to figure out what you've got. Yep. I'll write down the next one for you too. If you figure that one out, you want to go to the next one. Here's the next one. One's gonna be kind of gross, not gonna lie. yeah, we're gonna do that too. What's time? We got time. Yeah, we got time. And after we do these, we'll do some more nonlinear stuff. Do that. Your first question should always be, do we have a what? Do we have a saddle? No. So no saddle. Stable. I like looking at stability or instability first. I don't know why. That's just my preference. Probably because it's easier to see. Because to actually know if it's a spiral or a node, you have to like think about the whatever thing. So stable or unstable? Unstable. Tau is greater than 0. So we have instability. Okay. Spiral or node? I think it's a spiral. Let's check. Tau squared minus 4 delta is 6 squared minus 4 times 32. You don't, sorry, 4 times 13. Where'd the 32 come from, James? I know where it came from. You don't actually have to calculate this, 36 minus 52. Once you see that it's positive or negative, you can stop there and say, okay, I know that's negative, meaning I'm taking the square root of a negative number, meaning my eigenvalues are imaginary, meaning we have a spiral. We have an unstable spiral. Okay, we'll do maybe 2 more. Maybe no, we'll do 2 more probably. All right, trace here. Sorry, here's my new one: negative 9, 7, negative 14, 12. The trace should never be that hard to calculate. The determinant sometimes can be a real pain. So here my determinant is negative 9 times 12 minus 7 times negative 14. Ugh. Okay, so let's see here. If I calculate that, 9 times 12 is 108. Yeah. So not 144 like that one time when I did it. I know. I'm sorry. You guys still are traumatized with that. And 7 times 14 is 98. And 108, negative 108 plus 98 is negative 10, which is negative. So our first question, do we have a saddle? Yes, done. Saddle. Cool. Notice for all of these, we have not found any of the eigenvalues. That is totally fine if we're asked just to classify and not told anything about how we are expected to do it. Let's look at one more, and then we'll kind of, I'll remind you of the cool graphical thing that's in the book. Where'd my last example go? Which one was it? Was it that one? That one? I think it was that one. Let me double check here. Yeah, it was that one again. Let's say our last one here is 1, 2, negative 13, negative 9. All right. Do this one as well. Classify that equilibrium. Sorry, when I say that equilibrium, I mean obviously the origin, because the origin is the equilibrium of the system. Classify it. Let's another cool example, something too. Maybe I'll hide you away. I feel like I have. Fine. All right, so let's see here. The trace is going to be 1 plus -9, which is -8. And the determinant is going to be 1 times -9 minus 2 times -13, which is -9 plus 26, which is 17. 17, yeah. Okay, so certainly not a saddle. We know it's going to be stable because our trace is negative. Right, not a saddle, determinant is greater than 0. Stable, trace is less than 0. And then spiral versus node, well, let's see. So if I take, yeah, I really like the whole delta being bigger than or less than 1/4 tau squared is just not the way I like to do it. You can do it that way if you like, it's totally fine. But I'm just going to be calculating tau squared minus 4 delta. That just feels easier to me, I guess. That's going to be 64 minus 4 times 17. And I'm pretty sure 4 times 17 is bigger than 64 because it's 17 times 2 is 34 and 34 times 2 is 68. And 64 minus 68 is negative. And since that quantity is negative, it means we're taking the square root of a negative. So we have imaginary things, which means we have a spiral. If you prefer, you could have said it's going to be a spiral because your, oh my gosh, can I? Maybe, because your determinant is bigger than tau squared divided by 4. Because your determinant, which is 17, is bigger than -8 squared over 4, which is 16. That would be an also equivalent way of doing it. It's just not the way I see it personally. All right, so here's the picture that people often refer to when doing this sort of thing. Your horizontal axis is tau. I know I've mentioned this before, but I'm going to say it again. And your vertical axis is delta. And then this parabola here is the parabola. Ooh, can I draw it? Yes, maybe. That's the parabola where delta is equal to tau squared over 4. So if you're above that parabola, meaning delta is larger than tau squared over 4, well, when delta is larger than tau squared over 4, we have a spiral. So up here is spiral land. And specifically, when tau is positive, you have unstable spirals over here. The book is nicer though, because they like draw little cool pictures. Like in that section, they draw like an outward going spiral, like or a outwards, maybe yeah, outwards the right word, yes. An unstable spiral. And over here we have a stable spiral. And then right in the middle here, if you happen to have a 0 trace, you do have a node, a center, or a what's the other word there? A center or a, I feel like there's another word for it. Maybe I'm just crazy. Neutral spiral. Thank you. I could not think of the word before spiral. I was like, it's something spiral, but good God. Yeah. A center or a neutral spiral. And then down here, we have our unstable node or our stable node. Again, notice on the left where tau is negative, we have stability. On the right where tau is positive, we have instability. And then finally, down here in no man's land, we have saddles. Saddle land. So if your determinant's negative, you get this out. This picture is often referred to. You should at least have seen it a couple times now. You don't have to know it, but it's just kind of, people like it. So that's why I'm showing it to you, because it's kind of neat. All right, so yeah. I would hope not, but it's, again, maybe. Looking, I mean, if you look at, I would say her practice exams are similar enough to her actual exams that if you look at the practice exam for next week, you have an exam, right? Wednesday, you should be able to get a good idea of, again, and I'll look too to see, but my intuition is no, that you'll just be asked to classify, but not based on doing one more. Now, you might be asked to classify and you might only be, so I can see a way of doing it. I'm going to amend my answer. My answer is maybe, because maybe she's going to tell you, you have some system. I'm not going to give you the system. The trace of that system is 5. The determinant of that system is -2. What do I have? And then that's the only way you can do it, is by doing it this way. So my answer is a strong maybe. But I'll go look at the practice exams as well and just kind of see. Speaking of next week, the plan for next Tuesday is to review for your exam that is on Wednesday. So you all should come with questions on Wednesday. I will come with the practice exam so we can go over any questions about them you have or anything else you want to ask about. Oh yeah. So I will point out that showing that this is greater than 0 is literally equivalent to showing that the determinant is less than the trace squared over 4. Those are the same thing. I just happen to find this thing easier to remember than that. I find this easier to remember because I know that that's what's in the discriminant, and I know it has to be positive to have real eigenvalues, and it has to be negative to have complex eigenvalues. Where this one, I never remember which way the inequality goes. That's not true. I remember it now because I know which part of the graph it needs to be. So I know that delta needs to be less than, because I have to be under for nodes, and delta has to be bigger than, so I have to be above for spirals. But honestly, I only remember that because of the graph, not because I actually remember which way the inequality goes. But to answer your better question, no, either way is fine. All right, let's go ahead and look at some systems of nonlinear differential equations, which we talked about. We did a couple examples last time. Let's do a few more examples. So again, the idea here is you're just kind of adding on an extra thing. Instead of having 0, 0 being the only equilibrium, and then finding if it's one of the 6 different things it can be, now we're going to have to find multiple equilibria, find the Jacobian matrix, and classify each equilibria based on the Jacobian. It's really the same work, just more of it. So let's look at which example should I start with here? Where'd you go? Example that I want to start with? Good question. You're right there in front of me. So let's say we have the following. dx1 dt is equal to, I feel like we did this one. No, I guess we didn't do this one. Okay. -5x1 plus x1 times x2, and dx2 dt is equal to x2 minus 5x1 x2. And I'm going to point out, if you're doing these nonlinear differential equations, and you can tell it's nonlinear because we have x1 times x2, or because you have x1 squared, or because you have x2 squared, or because you have some not just constant times one variable term. If you have that, it's nonlinear. When you have something nonlinear, you should do yourself a favor and say that the first one is f, and the second one is g. You could write f of x1, x2 if you wanted to, and g of x1, x2. You don't need to, though. All right, so first things first, let's find all the equilibria. Oh, yeah, of course. Let's find all the equilibria by setting each of these equations equal to 0. And actually, before we set them equal to 0, let's help ourselves out and factor. So from this first equation, I can factor out an x1. I'm left with a -5 plus x2. From the second equation, I can factor out an x2, and I'm left with a 1 minus 5x1. Okay, so in my first equation, I either get x1 equal to 0 or -5 plus x2 equal to 0, meaning x2 is equal to 5. I cannot stress enough, 0, 5 is not an equilibrium. Because if you plug in 0 for x1 and 5 for x2 in this other equation here, it's not equal to 0. And both equations have to be equal to 0 at the same time. What this is giving us is half of a critical point. x1 equal to 0 is half of a critical point. I need to find the x2 value that goes with that. So what that means is I'm going to plug in x1 equal to 0 into this equation and then find what x2 needs to be. So if x1 equals 0, Well, then I have x2 times 1 equal to 0. So I'm going to get x2 equal to 0. So one of my critical points, not surprisingly, is 0, 0. Equilibria, critical point. I'm probably using the critical point not the right way, but sorry. So one of our equilibria is 0, 0. 0, 0 is almost always an equilibrium. It's a pretty good bet. Occasionally there are weird problems where it's not, but I don't think you have any of those, so we're not talking about it. Or we could have picked x2 equal to 5. Well, if x2 is equal to 5, then this equation becomes 5 times 1 minus 5x1 equal to 0. Divide both sides by 5, or just set this part equal to 0, and you get 1 minus 5x1 equal to 0, 1 equal to 5x1, x1 equal to 1/5. So my other critical point is 1/5, 5. And if you want to check, you can plug either pair of points back into the original system of two equations and get this one equal to 0 and that one equal to 0. I'm going to pause you, actually. So what I would say is it really depends. Sometimes you have something like this where your first equation gives you a value for x1 and for x2, and then we use each of those in the other equation. Sometimes other things happen, though, where you might not even get values for x1 or x2. You might get like a relationship. You might end up getting like x1 equals 3x2, and then plugging that into the other equation and solving for x2, and then plugging your value for x2 back into that equation to get x1. So the thing is really, it kind of depends. And that's why we're going to practice a few other things as well. So now what? If I'm in equilibria, I need to test them by putting them into a matrix. But the matrix I need, I haven't found yet. So the matrix I need is the Jacobian. So the matrix we want is the Jacobian. And that's just the matrix of partial derivatives of f and g. So it's f differentiated with respect to x1, and then f differentiated with respect to x2, and then the same thing but for g's. So the partial of g with respect to x1, the partial of g with respect to x2. In each row and column, something should be the same. So right, in the first row, you get f, in the second row, you get g, in the first column, you get x1, in the second column, you get x2. All right, so then my Jacobian is going to be, so the partial of f with respect to x1 is going to be -5 plus x2. The partial of f with respect to x2 is going to be 0 plus x1. The partial of g with respect to x1 is going to be 0 minus 5x2. And the partial of g with respect to x2 is going to be 1 minus 5x1. And then we plug in each of our equilibria, and then we classify them in any way you want. So if we look at j of 0, 0, our matrix is going to be -5, 0, 0, 1. Okay, if your matrix looks like this, I definitely think you should do it just by knowing what the eigenvalues are, because if your matrix is like this, you know what the eigenvalues are. What are the eigenvalues? Perfect. So what do we have? Stable node, an unstable node, a saddle, a spiral. We have a saddle, right? Because when the eigenvalues are the opposite sign, it's like the determinant being negative. In fact, it literally means the determinant is negative. Oh yeah, lambda equals -5, lambda equals +1. You have a saddle. Let's look at the other equilibrium. J of 1/5, 5. Plugging that into our Jacobian, we get -5 plus 5, which is 0. We get 1/5. We get -5 times 5, which is -25. And we get 1 minus 1/5, which is 0. Now be careful here. The eigenvalues are not 1/5 and -25. That thing only works if you have a 0 in this corner or this corner. These two corners are not helpful to have zeros in as far as easily identifying the eigenvalues. Oh, there's a chat. Let's see. When classifying equilibria from the Jacobian matrix, the book mentions that we should look at the larger of the two eigenvalues of the Jacobian to classify the equilibria. Does this apply here? That's a good question. I don't know. That doesn't. I'm not sure, Mahmoud. Yeah, I'll have to go take a look, to be perfectly honest, because I'm always thinking about it just based on the usual kind of looking at both eigenvalues. Yeah, I'm curious about that. I don't know. I'll go look at that. If you wanted to message me or email me what specific section of the book it is, or maybe what page number that's on, just to make it easier for me to find it. But I will definitely go take a look at that and try to figure that out. Sorry, I don't have any answer for you right at the moment, but I don't actually know. Okay. So here we could find the eigenvalues, or we could do the trace determinant method. Ooh, interesting. What's the trace going to be here? And the determinant's going to be positive. So I think that means we're going to have a neutral spiral. Well, let's find out. Let's actually find the eigenvalues. But right, here's them. Yeah, I mean, that would make sense, right? Because if you look back at our little graphy thing here, right? If your trace is 0, it means you're on the y-axis. But our determinant is definitely positive because it's 0 minus a negative number, which means we have to be up here in center or neutral spiral. Cool. Well, let's go ahead and look, because I think it's worth doing the work. The other thing is you have to do enough work that you can convince the person that you know what you're doing, right? If you just wrote neutral spiral here and didn't write any like justification, probably not going to fly on an exam. So I would probably be like, okay, well, my eigenvalues are going to be determinant of negative lambda, 1/5, negative 25, negative lambda. That's really easy to solve, though. You just get lambda squared minus 1/5 times negative 25, which is negative 5. And then lambda squared plus 5 equal to 0. Oh, yeah, we're exactly getting lambda squared equal to negative 5. So lambda is equal to plus or minus the square root of negative 5, which is plus or minus I root 5. My eigenvalues are imaginary, and the real part is 0, meaning I have a neutral spiral. Cool. Oh, shoot, I forgot to plug in. Because why do I have a spiral? Anybody, why do I have a spiral? Because my eigenvalues are imaginary numbers. Why is it not unstable or stable? Right, exactly, because the real part is 0. Cool. Let's do, yeah, we got time for one more. Let's do one more. Where'd you go? Yeah. You're welcome. Let's do that one. Should be pretty good. I think that one's pretty good. Yeah. All right. Oh, question or chat. Let's see here. Or is it just the page number? Yep. Thank you. I'll take a look at that. Thank you, Mahmoud. I appreciate it. 669. Okay. So let's say we've got the following. dx1 dt is equal to, we'll do that one. x1 minus 2x1 squared minus 6x1 x2. That seems terrible. And dx2 dt is equal to 2x2 minus 8. x2 squared just looks stupid. And then minus 2x1 x2. Again, let's call the first one F, the second one G. I think it's just a good strategy in general. If you're going to do this, call that first one F, call the second one G, just so you don't forget. And then I'm going to factor. Notably, each of these pieces has an x1. So I can factor out an x1 and I'm left with 1 minus 2x1 minus 6x2. Similarly, here I can factor out an x2. I'm left with 2 minus 8x2 minus 2x1. So I got a couple things going on here. From my first equation, I'm getting either x1 equal to 0 or 1 minus 2x1 minus 6x2 equal to 0. From my second equation, I'm getting x2 equal to 0 or 2 minus 8x2 minus 2x1 equal to 0. For each of these equations, one of these two things has to be true. Because as long as that's equal to 0 or that's equal to 0, the whole first part will multiply to 0. Same deal over here. So we have essentially 4 pairings. We can either do these two guys together, or these two guys together, or these two guys together, or these two guys together. Because any choice of one from here and one from there will get us both equations equal to 0. So let's look at the easy one first. Our easy ones are going to be 0, 0 is the easy one. That's when x1 equals 0 and x2 equals 0. And then let's look at x1 equals 0 and 2 minus 8x2 minus 2x1 equals 0. But if x1 is 0, then x1 is 0. And you're left with 2 minus 8x2 equals 0, which becomes 2 equals 8x2, which becomes 2 over 8, or 1/4 equals x2. So another critical point is going to be 0, 1/4. And then let's do the opposite pairing. Let's pick x2 equal to 0. And I need one of these. I already have used that one, so I have to use that one now. 1 minus 2x1 minus 6x2 equal to 0. That goes away because x2 is 0. Left with 1 equal to 2x1, or 1/2 equal to x1. So 1/2 comma 0 is also a critical point. And then finally, the one that's usually the most annoying is setting both of these two equation-y ones equal to 0. So if we do that, we're going to have 2 minus 8x2 minus 2x1 equal to 0, and 1 minus 2x1 minus 6x2 equal to 0. I'm noticing that both of these equations have a minus 2x1 in them. So what I would probably do is, in this equation, solve for 2x1. Say, okay, 1 minus 6x2 is equal to 2x1. I'm not even going to divide by 2. I'm just going to take what 2x1 is equal to and substitute it in for 2x1 there. So then I'm going to have 2 minus 8x2 minus 1 minus 6x2 equal to 0. And then solve for x2. So 2 minus 8x2 minus 1 plus 6x2 equals 0. 2 minus 1 is 1. Minus 8 plus 6 is minus 2x2. So I'm going to get 1 equal to 2x2, or 1/2 equal to x2. I'm going to plug that back in up here to get 1 minus 6 times 1/2 equals 2x2. 6 times 1/2 is 3. 1 minus 3 is negative 2. So x2 is, sorry, x1. Apologies, that's x1. That's terrible. X1 is going to be negative 1. So my last critical point is going to be x1 is negative 1, x2 is 1/2. Then we have to take the Jacobian and plug in all those points, and we're almost out of time. So let's just find the Jacobian, and then we'll talk about what we do here. So looking at our f and our g, our Jacobian is going to be, sorry, you'd like to see things maybe. So fx1 is going to be 1 minus 4x1 minus 6x2. fx2 is going to be 0 minus 0 minus 6x1. gx1 is going to be 0 minus 0 minus 2x2. And gx2 is going to be 2 minus 16x2 minus 2x1. So then plugging in your critical points, sorry, or your equilibria, J of 0, 0 is 1, 0, 0, 2. Oh, look, that's pretty easy to classify. That's going to be an unstable node because our eigenvalues are 1 and 2. I'm not even going to write that down because I just want to write the rest of these and then you can explore what's happening on your own. J of 0, 1/4 is going to be 1 minus 6/4 is 1 minus 3/2, so negative 1/2, and then 0, and then negative 1/2, and then 2 minus 4 is negative 2. Looks like we'd have a stable node there because both eigenvalues are negative. And then J of 1/2 comma 0 would be 1 minus 2 would be negative 3 would be 0, 2 minus 0 minus 1. So we have a saddle. It's a good problem. Getting something, one of everything. And then finally, J of the last one, which was negative 1 comma 1/2. It's probably the one you have to work for. You plug in negative 1 for x1 and 1/2 for x2, you're getting 1 plus 4 is 5, minus 3 is 2. You're getting a negative 6 times negative 1, so positive 6. You're getting a negative 2 times 1/2, so negative 1. You're getting a 2, minus 16 times 1/2 is minus 8, so 2 minus 6 is negative 6, and then plus 2 is a negative 4. So that's the last one. That one you'll actually have to work for to find the eigenvalues. All right, I should stop talking. It's 1:31.